Welcome. Today we'll be discussing section 6.2. Topics include ellipses, standard position of ellipses, and standard ellipse equation. For the definition of ellipse, we have given two distinct points f and f prime and some real number delta, which is greater than the distance between f and f prime. The ellipse with foci f and f prime with width delta is the set of points P where we have the distance between the set of points and F plus the distance of that same set of points and F prime is equal to the width or delta. So what does this mean? Well, if we have an ellipse, how we can generate this set of points P is because we have two foci, F and F prime. And then we'll have this vertical line. Well, it doesn't necessarily have to be vertical. Let me just draw these. And for the larger distance between this point and this point, we'll call these the vertices. So we'll call V and V prime. And the others we'll have M prime and M. And we'll denote where these two axes intersect as the center. And now to round this out, we'll call this distance B, we'll call this distance A, and we'll call this distance C. So in other words, what will happen is we have the foci, we have the vertices, we have the minor points, we have the center. B is the distance between the center and a minor point. A is the distance between the center and a vertice. C is the distance between the center and a foci. So what are some formulas that we can get from this? We have the width, delta, is equal to 2a, which equals the distance between V and V prime, which should intuitively make sense. We're taking this delta, and if we take the distance between V and V prime, that will certainly equal it. And since A is defined as from the center to the vertice, it's halfway, which then arises to this equation. Well, the focal distance this is another term for C. We get the following equation of C squared equals A squared minus B squared. Another way to think about this is if I added the B squared to the other side, I have B squared plus C squared equals A squared. That looks like a Pythagorean identity. It really is. If I just take this A, I rearrange it to be here, I'll get my right triangle. And it works out as you expect it would. So let us talk about the standard position of an ellipse. The reason why we are talking about the standard position is because we can describe the ellipse from just these sort of tendencies of what we've labeled in the example. And for reference, I'm going to call the ellipse E, and I'll refer to it as such. So for ellipse standard position. We have either ellipse E with center Z of x naught, y naught. It either has an H major axis or it has a V major axis. Now, with an H major axis, we'll have x minus x naught squared all over a squared plus y minus y naught squared all over e squared is equal to 1. Now, as I've drawn the ellipse here, this is a horizontal major axis. And so we can see that the A is measuring this horizontal distance, the B is measuring the vertical distance, and they're kind of paired here, with the x's being horizontal and y being the vertical. Well, in a vertical major axis, we have x minus x naught squared divided by b squared plus y minus y naught squared divided by a squared, and set this equal to 1. So the reason why that the labeling changes of A and B is because if we rotate this 90 degrees, what ends up happening is that our A is now a vertical distance. And so we have to count for that. So what does this mean? Is that we have to include that A is always greater than B. We want the greater distance, and then from there we can label which is our major, which is our minor. So with this, we'll have some additional properties of our vertices. We have them at x naught plus or minus a times, or sorry, with y naught as the other point of the entry. We have our foci, and they are at the points x naught plus or minus c, y naught, and our minor points we'll have at x naught plus or minus, oh sorry, x naught, then we'll have y naught plus or minus our b. And we're really just kind of labeling here as our center. We're going to label as our x naught, y naught. And now if we go plus a, minus a, we're at our v's. If we go plus c, minus c, we're at our f's. If we go plus b, minus c, we're at our m, or our minor points. And that's for our horizontal. Again, rotate this, come up with the same sequence of equations for our particular points for a vertical horizontal or a vertical major axis. So our vertices are at, we'll have x naught y naught plus or minus a. Our foci, that will be at x naught, y naught plus or minus c. And then our minor points we'll have at x naught plus or minus b, y naught. For your check on learning for this video, write down this ellipses standard position. Include that you need the condition that A is greater than B. In fact, include that, underline that, box it in, circle it, identify that this is a necessary condition. We have to have this condition, otherwise we're going to get our A's and B's backwards and the ellipse is going to be rotated and we don't want that. So let's go over some questions. Example 1. We have find the equation of the ellipse with the vertices v of -2, 1, v prime of -2, 5, and we have f of -2, 2, and that's all that we're given. So we're given that we have our vertices, and they called them our vertices. So we have a axis that our x's didn't change, but our y's changed. So for a mental picture, we should be thinking that our ellipse looks something like this. Because we're at x -2 and -2, 5 up here and -2, 1 down here. So when we're thinking of this, we should say, okay, what do we know? The first thing that we know is that we have a vertical major axis. So that means we have x minus x naught squared over b squared plus y minus y naught squared over a squared equals 1. We should be able to write this down right away. And again, we know it's a vertical because we said that we have the vertices here, and so we know that it is a vertical major axis. So now well, our center is our midpoint between our axes. So we'll need the distance of v prime, which equals, we're going to have square root of 5 squared plus 1 squared is equal to 25, 26, square root of 26. No, sorry. I messed this up. We'll have square root of -2 minus -2 squared plus 5 minus 1 squared. -2 minus -2, that goes to 0. And then 5 minus 1, 4, 4 squared, 16, square root of 16 is 4. So that is our delta. We want to find our midpoint, so we can either use an equation, use a midpoint equation from an algebra class, but what we can also do is get our A is equal to 1/2 times our delta, because 2 times our A is equal to our delta, which that means we have A equaling 2. We know that our vertices is our y-coordinate, y0 plus or minus A. So here I have to go down to, here I have to go up to. So my y0 is equal to 3. My x0 must be -2 because that hasn't changed. I'm on this vertical axis. So that means I can now write down my center. Z is of x0, y0 is equal to 3, sorry, -2, 3. So now we can find our C. So C is equal to, and we have our C is to our foci. So we have this equation here, x0 plus or x0, y0 plus or minus C. Our foci is, if this is -2, 2, and we have one at 1, -2, 3. -2, 3, and we have one at 1 at f equals -2, 2. So f equals -2, 2. So here is our f. Our distance between this two is 1. So our C is equal to 1. So that means we have C squared is equal to A squared minus B squared. We can substitute in, we have 1 squared is equal to our A, which is 2. So 2 squared minus B squared. Solving for B, we get 1 minus 2 squared, which is 4. So that's -3 divided by -1. So we get 3, take the square roots, and we'll have B is equal to square root. So we can now describe our equation, and we have x minus x0, which is -2. So we're going to do x plus 2, quantity squared, divided by our b squared, which is square root 3 squared, is 3, plus, and we have y minus y0, which is 3. Square that quantity, divided by a squared. A is 2, 2 squared is 4. It's equal to 1. And there is our standard equation for the ellipse that has vertices at -2, 1, -2, 5, and a foci at -2, 2. So we have an equation, but we're now going to talk about a standard equation. So this is now the standard elliptical equation. we have a times x minus h squared plus c times y minus k y squared is equal to capital M. Note that a and c cannot equal 0 and are same sign. Meaning if one's positive, the other's positive, one negative, the other's negative. We have some conditions that A, if M is equal to 0, then the equation is a point H. Okay. In other words, what happens is if this is 0, this whole equation reduces down to just H and the point HK. It's the only thing that can satisfy it. And that makes sense. If we plug in H for X and K for Y, we get 0 squared times A, that's all 0. Here we get 0 squared times C, that's all 0. 0 plus 0 equals 0. So it basically reduces it to how far away from your point. If the only point is a singular point, well, you can't go any further than 0 if you're already at that point. Okay, so another thing is that if M does not equal 0 and is of opposite sign, then, or of A, then we have no solution. So if this is negative and A is positive, because A is positive, C must be positive. If we have positive plus a positive, there's no way we can get a negative. If we have this being positive, this being negative, this must also be negative. Negative times negative, we're going to get a negative, and it makes no sense. So the only way that we can get an ellipse is when we have M, C, and A all being the same sign, meaning they all have to be positive, they all have to be negative for it to work. And if M does not equal 0, we then have the last condition of M being of same sign as A, then we have an ellipse, or we have a circle. And we have an ellipse if A does not equal C. We have a circle if A equals C. So where before we required the standard position for it to be an ellipse, that we could not get a circle because we had to have this condition of A being greater than B. Now we're generalizing this so that we could have a circle. And if you want to put it in this frame, a square is a rectangle, but it's just a special type of rectangle. A circle is an ellipse, but it's a special type of an ellipse. So let's work with an example with this terminology. And we'll start off with example 2. We want to find all the points of interest. So that's the center, foci, vertices, minor points. And we're given 9x squared plus 16y squared minus 18x plus 64y minus 503 is equal to 0. So it starts off with a mixture of different powers, and so we will want to try to put it in this sort of form. So let's try and complete the square first. So when we complete the square, we're going to have 9x squared. When I factor out 9, I'm going to have minus 2x plus something here. I'll get to what this something is in a bit. And then we're going to add, we're going to factor out 16. We'll have a y squared plus, and for here, 16 times 4 is 64, so we'll have 4y plus something here. And we're going to have this equal to 503. Now, if you've kept the 503 on the same side, it doesn't really matter at this point. Well, what we want to do is just be consistent with what we're doing. So if I was to complete the square, I would want to have half of the center term and then square that. So here we'd have -1 squared is 1. So I'm going to insert a 1 here. Now by inserting a 1 here, we can now reduce this to being x squared minus 1, or sorry, x minus 1 quantity squared. That's the point of completing the square. However, we have this 9 out front. So we have to account that we basically added 9 to this equation. So we added 9 to the left side, so we're going to add 9 to the right side. Another way of thinking about this is that we added 9 to the left side, so we have to subtract 9 from the left side. Either way will work as long as you're consistent with what you do. So for the 16, we have 4y, 4 divided by 2 is 2. Square that and we get 4, so I'm going to put a 4 here. What does that reduce to? Well, y plus 2 quantity squared will get us this expression. So we have a 16 out front, so we can't forget that even though we have a 4 here, it was really 4 times by 16. What is that? 64. So we essentially added a 64 here, so we have to add a 64 here. Okay, well, let's fill in the plus there, equal sign here, and we get 576 for the right-hand side. So now we have an equation we can check. We have our A, we have our C, and we have our M. All of them are positive. Our C does not equal our A, so that means that we must have an ellipse. So we're here, they're all the same sign, that's great, but we have A not equal to C, so we must have an ellipse. So what we can do is generate that ellipse equation. We know that the equation starts off with a 1 on the right-hand side. So let's divide by 576 and divide each one of these by 576. 576. And when we reduce, we'll get x minus 1 quantity squared, and we'll get 64. Well, we want this and get our a's and b's. So what is the square of 64? That is 8. So I'm going to write this as 8 squared plus, and we're going to have y plus 2 squared all over, and we're going to have 36. Well, that is 6 squared. This is equal to 1. So now, when we tabulate our information, we can say that, all right, our center, z, x naught, y naught, this center is equal to 1, negative 2. Because again, we have to think of y minus y naught. So this is y minus a negative 2, or y minus a negative 2. And so then our vertices, I'm just going to label them as v. We now have to think of, all right, actually, let's do this first. Let's do, what is our a? Our a equals whichever one is bigger here. Well, that's 8. Our 8 is underneath the x's. So we must have a horizontal. So let's fill this in with our b is equal to 6. And now for our vertices, we're going to have our x1 plus or minus our horizontal, which is a, and then our y, which is just negative 2. Our foci are at 1 plus or minus our c, which our c we can calculate to be 2 square root 7, negative 2. And again, that is calculated because we have c squared equaling a squared minus b squared. And then our minor points, or m, little m, is equal to 1 plus or minus 6. So this information that I'm putting a bullet point next to is what we're needed. However, it's not bad to include our c of 2 square root 7, just to include all the information. However, the bullet point is the only thing that was required in when I say find all the points of interest of the ellipses. One thing to note is that these can be, we can write these as 2 different points. I shorthanded it, but on a homework or exam, I would think it would be highly preferred to actually write this as 9, negative 2, and negative 7, negative 2 as 2 points, and both those are vertices. Similarly, we have the foci being at 1 plus 2 square root 7, comma, negative 2, and 1 minus 2 square root 7, comma, negative 2. And then our minor points are at 1, 4, and 1, negative 8. Okay. With that, that is all the content I'm covering in 6.2. Thank you for watching and have a great day.